Hello, everyone. My name is Riccardo Balin. Today we'll be talking about how we can integrate AI and machine learning and simulation here at ALCF. Maybe a little background. I'm a postdoc here at ALCF. My background is in large-scale computational fluid dynamics and turbulence modeling. But more recently, I've been diving into scientific machine learning, still applied to CFD. And then especially coupling simulation, large-scale simulations with machine learning. So let's start maybe with a little motivation. Why would we want to couple simulation and machine learning? I think there's a lot of reasons. We could try to substitute some inaccurate or expensive components of our simulation with machine learning models. So that goes into the fields of closure modeling or surrogate modeling. We may also want to control our simulation with a machine learning model, perhaps selecting the numerical scheme to use, or maybe even the input parameters for our simulation. Another advantage is that we can try to avoid AI bottlenecks and disk storage issues when it comes to generating training data for simulations and then using that to train a model afterwards. We can do the two things together or in situ, or online is another way to call that. And so by streaming the data from one component to the other, we can avoid some of these issues. We can also try to fine-tune some of our models online. So say we have a pre-trained model based on some offline training we've done. Perhaps the simulation can give us access to new training data that is important to include. And so we could do that again online by integrating the two. And then finally, perhaps an exciting area of research is active learning. So how do we continuously improve our machine learning model as the training data and the simulation progress? Now, how do we then couple simulation and machine learning? I think there's perhaps three main aspects of this coupling to think about. The first one is physical proximity. This actually relates to where the different components are located on the hardware. So we could have all of them sharing the same nodes. So this would be like this sort of schematic here on the left, where you can see all the three components, the machine learning, simulation, and in this case, there's also a database. You can see they're all within the same nodes. And so communication between the components is now contained within the node. We can also try to use spread the components to have different nodes, but keep them on the same machine. So now this would be sort of this diagram on the right, where you can see now a different set of nodes is used for the three different components, and now we are communicating data through the machine's interconnect. But finally, there's also another option, which is to run the components even on separate machines. This could be, say, running the simulation on Polaris, and then the AI component could be on the AI testbeds. The other thing to think about is data access. Here we can split it into direct and indirect. In the direct case, the components share the same memory space. So this would allow for a zero copy data transfer from one component to the other. And in the indirect case, we have the components using different logical memory, which means that we do have to copy data from one component to the next, perhaps even doing some data transfer. But in either way, something to think about when coupling simulation and AI is that this generally requires frequent synchronization of memory between the components or movement of data from one to the next. The last of the third, I would say, aspects to think about for this coupling is the execution management. Time division or tight coupling is perhaps the more immediate solution to think about. This means that the components run on the same compute resources, may even use the same processes. So here, for example, on the first diagram on the right, you can see that the machine learning component is embedded within the simulation. So this is also often called Python or machine learning embedding. But this usually leads to a staggered in time workflow, where the execution of the simulation is then halted by the machine learning and vice versa. So this may allow for the direct memory access that we mentioned earlier and not copying the data from one component to the next. But there's usually a significant amount of idle time as you switch from one task to the other. Instead, we can do space division or loose coupling. And here the components run on separate compute resources, as you see here on the diagram on the right. So now we have the simulation taking up 2 of the GPUs on the node, and then the machine learning component taking up the other 2. So this allows for concurrency in time, meaning that the components can run simultaneously. This allows then for minimal idle time, meaning that there's no significant blocking operations except for perhaps the data transfer, say to a database or from one component to the other. But usually this means that the data does have to be copied and transferred from one component to the next. So there's a couple different software packages that you could use to implement either tie coupling or loose coupling. For tie coupling, there's been a number of examples even done here at ALCF. For example, we have worked on embedding Python and the machine learning frameworks into various CFD codes. The Python foam and TensorFlow foam are good examples that are already at the ALCF repository online. But there's ongoing work into doing something similar into NecRS, which is a more modern CFD code that utilizes GPUs and scales very well. So it's actually being, it's tested for Polaris and it's being prepared for Aurora. And this work was led by Ramit Malik, Samuel Patel, and Bethany Lush. The other approach, which was also mentioned this morning, is we could try to link our simulation code directly with some of the C++ libraries available out there, specifically for inferencing. So we could use libtorch or Onyx runtime on Polaris, and we can call these from C, C++, and Fortran codes. And a note here for Aurora, looking ahead, libtorch will be supported, but what is actually perhaps going to be the main or a good thing to explore over there is Intel's new inference library called OpenVINO. So it's not available for Polaris, but it'll be something to keep in mind moving on to Aurora. And usually something that I have a little note here, usually this tie coupling is more performant and preferred for inferencing workloads. This is because we can usually do a zero copy of the data from one so the simulation to the machine learning component, and this allows for much faster deployment of the model. The loose coupling, or no coupling at all actually, can be done with a couple different libraries. SmartSim and SmartReady is one of them, and that's actually what the rest of the talk will focus on. But there's also a few other options out there. There's ADOS2, which came out of the exascale computing project. Dragon is another tool coming out from HPE. Dragon is quite new, but we're starting to test it here at ALCF as well. So there might be some upcoming workshops or information about that. And then finally, I'll note that usually loose or no coupling is preferred for training. This is usually because it allows 2 tasks to run, or even more than 2 tasks to run concurrently. And there's greater flexibility in setting up the workflow, which usually for training requires a little bit more complexity. So pros and cons for either. Now, the rest of the talk, I wanted to spend basically going through a demo on how you would try to do this coupling between simulation and AI using SmartSim in this case. So we can start with a little bit of background. SmartSim is an open source tool developed by HPE, and it was designed effectively to do exactly what we're going to be doing with it today. Couple simulation and machine learning workflows. There's 2 main components. There's an infrastructure library, and this is really a set of Python APIs that allows us to basically set up the workflow. And so determine, how many components we have, how big our simulation is, and our training applications are. This interfaces with the scheduler, so we can launch jobs on Polaris through PBS Pro, and then Cobalt on Data and Data GPU. And this is, I mentioned a database in the past. This is one of the key components of SmartSim. And so the infrastructure library also allows to deploy this database. And you'll see how it's being used in a second. The second component is SmartRedis. This is really the client library that you would then call from your simulation and allows you to communicate to the database. And there's APIs for Fortran, C, C++, and Python. So as I mentioned, this is what allows to move data to and from the database, and then also run models on the database, as we'll see in a second. So one of the big things we can do with SmartSim is online training. So this idea of training a model concurrently as the simulation is running. The diagram here basically shows how it's set up. You have a simulation, in this case a CFD one on the left. We can initialize a Smart Redis client on each rank. Each rank then computes its contribution of the overall domain and therefore the training data, and can send this to the database where it's stored in memory. So this is done avoiding the file system. And then on the other side, we have a distributed training program. On each of those ranks, we can also initialize the client, and then we can talk to the database. So effectively, we have a flow of data from left to right, in this case, from simulation to training. But this allows us to basically fill up the database with data as the simulation is going, and then the training is aware of that data being put onto the database, and therefore can keep training on it and update the model. Something to mention is that this is actually fully decoupled. That is, each component just really interacts with the database. It's just by setting up the entire workflow that you basically link up simulation and distributed training. And so the only idle time is the time spent from the simulation sending data to the database, but it doesn't really care whether the training is ready or not to accept that data, whether it will even be used. So the two parts are really distinct. And then finally, there's two components only in this diagram, but that's not a limitation of the libraries. You can have multiple simulations contributing to the training data and also train multiple models simultaneously. We can also do inference, which is important because once you've trained a model, then you would probably like to use it from the simulation. And we can also do this with SmartSim. In this case, we load a model onto the database. And then we have the simulation again connecting from each rank. We send the input data, we evaluate the model on that input data to get some outputs, and then we retrieve those back from the simulation. So the workflow is a little bit simpler, but this is compatible with most popular or the more popular frameworks. So we can use TensorFlow, TensorFlow Lite, Torch, and Onyx runtimes. Okay, so the other thing I wanted to mention about this tool is that it is quite scalable, and that's why I personally like it. We are able to do a co-located deployment, so effectively every component shares the same nodes. This means that we do not use the machine's interconnect to transfer data from one component to the next. Everything is limited within each node. This means we launch a database on each node, and then the simulation is distributed across the nodes as well as the training. What this allows us to do is actually get very good scaling to the full size of Polaris. So on the bottom left, we can see how the time spent sending and retrieving data to and from the database from the simulation is actually constant as we scale out, basically to the full size of Polaris. And then here in the middle, you can see sort of similar plots, but for inference. So in a weak scaling test, the cost is constant, and in a strong scaling test, it decreases linearly with the number of simulation ranks. So this is really good, which means that we can take our scalable training programs and also simulations and then apply this together. And then the overhead from the data transfer doesn't actually impact scaling. It effectively just applies a fixed cost to the simulation regardless of the size. Now, I wanted to also give a few more details on the demo. So this is all present in the workshop repository. I put this information in case you wanted to follow along. So you would go clone the repository or just maybe do a poll in case there's any new material you would like to get. But what I'm showing now is already there, and there's also information to follow along later on the repository. But I'll go through it now to maybe give an explanation of what's already there. So in case you want to follow along, just keep in mind to change directory to this coupling simulation ML /negHRS-ML directory, and then submit an interactive job. There's a script already there to do so. Another thing to note is that this requires a slightly different Conda environment or environment to run this tool. So this has already been built, and it was placed in the workshop project folder, so it's available for all of you to use right away. Unfortunately, this was based off of an older Conda module that is available on Polaris, but we have plans to actually integrate all of this into a module itself. So soon in the near future, the goal is to be able to incorporate all of this with the basic module that you get that has been mentioned in previous presentations. And you can also build your own. There's instructions on how to build all these different libraries, also at the workshop repository, in case you wanted to make your own Conda environment and test this out. So the goals of the demo that I made for this workshop is basically to use SmartSim and SmartRedis to train a machine learning model from an ongoing CFD simulation. So something we've sort of already mentioned that is capable of doing. And then the idea is, of course, to then call this model from the CFD code and do inference with it. And finally, we want to try to make good use of the GPUs on the Polaris nodes. So we're using an in-house fork of the NecRS code. I mentioned this code already. It is perhaps one of the most efficient and scalable CFD codes for GPUs and looking towards exascale out there. We've made a fork that is maintained here by ALCF called NecRS ML. And this is actually a sandbox that we're using to test different approaches for integrating the NecRS code with machine learning. So this example comes from one of the branches from that repository, but keep an eye on it because we are going to keep building and keep testing new approaches and then offer those for of course, all of our users to look at and use as examples. And then just to give a little bit of physical background on what exactly it is that we're trying to do here, we are trying to estimate the wall shear stress from a turbulent channel flow using the velocity at some location above the wall. So you can see here, this is the just a snapshot of the velocity for a turbulent channel flow. The goal is to use the velocity along this plane to estimate what the wall shear stress, which is basically just the velocity gradient times the viscosity at the wall. The reason why this is actually a relevant problem is because due to the smaller turbulence scales that we have near the wall and also the high velocity gradient, most of the elements in our mesh are actually located very close to the wall. So by implementing a model to estimate that shear stress, which is the boundary condition effectively to the domain, then we could, in theory, be able to avoid resolving with our grid that area. And so this allows us to get to larger Reynolds number or to larger flow domains and effectively get to more interesting problems. And this is already being done in the community. So this is just a sort of an easy example of this task. So first, of course, we want to start with training. Again, in case you're following along or just for future reference, you would want to move to the train_example directory that is in the repository, source the environment, and then just do a /run.sh. This is if you have an interactive node. If instead you want to submit it as a batch script, you can do so by just doing qsub submit.sh. And all these scripts are already present in the repository. But then also to maybe dive into the details of what actually is going on in the example. So we have both NecRS and the training running in parallel. It's actually two processes each, just so that we can fit on a single node for this demo. And so we have NecRS running on the first two GPUs of the node. The database is then deployed on the CPU, as you can see here, and then we have the distributed training running on the other two GPUs. This is just one configuration, of course. We can actually deploy NecRS on the CPU and training use all the GPUs or vice versa. It's up to the user to determine how to configure this case. And what's going on is that every 10 time steps, NecRS is sending the training data, which, as I mentioned in the previous slide, is composed for the velocity at this plane and then the shear stress at the wall, over to the database. So you can see here from the necrs.out, this would be the output file that you would get running this demo. Every 10 time step, you should see this little output here saying copying solution to nec. And then importantly, it's saying sending field with key x.0.10 and then done. So what this means is that it's sending the input data, which I'm calling x, on rank 0, and then for time step number 10. And then after that's done, it actually sends the time step number. This is how the machine learning knows when new data has been sent to the database, and so when to include it into the training set. So similarly on the training model.out file, this is the output of the training script, and you should see basically the opposite side of that. You now are getting new training data from database. This happens as soon as new data is populated. And so it's saying here, for example, that this happens after NECRS sends the training data for time step number 30. It's saying added time step number 30 to the training data. And then for the third epoch, you can now see that rank 0 is grabbing the following keys, which means that it's actually a mix between data from rank 0 and 1 of NECRS and also the different time steps that have been sent so far. So this is how we keep basically mixing up the data and making sure that we can do basically stochastic gradient descent on the entire domain. So after that's done, and it should run, it should train the model just in a few epochs. For the simple example, then we can do inference. These are the instructions if you want to follow along or for future reference. And the deployment is very similar, but now we don't really have a distributed training program. We just have the database having access to a single GPU for inference. So what happens now is that every 10th time step, we take that model that we loaded at the beginning of the simulation, as I mentioned previously. NECRS is running in parallel on the 3 GPUs. And every 10 time step, each rank is sending to the database their input data. This is then being routed to the 4th GPU for inference, and then this produces some output, which is also marked with the rank ID. So then each rank can now go get its own output, and then the simulation progresses. And so from the NECRS.out file, you should then see these indication of everything going smoothly, saying, sending the field with key x.0. This is rank 0 sending its input data. It's then running the model and then retrieving the field with key y. That is the output. So this should also, I think it's set up to run for, say, something like 70 time steps, or it should do this 6 or 7 times. And then, something to mention is, of course, maybe we went a little bit fast, but some of the details about what exactly is going on, how to run this, are all present in the workshop repository. So there's a big README file with a lot of detail there, so you can go take a look to see how this is actually done, and especially how the driver script is set up, because this is what sets up the workflow for either the training or the inference case. And then also there's information there on how to scale it out to multiple nodes. The example in the demo is set up to just use a single node, so you can use an interactive session with just one node. It's easy to get and to test. But of course, as I mentioned earlier, this scales out really well, so you can change the parameters in the config file to then test this out on more nodes. And then that's all I have for today. So thank you, and I'm happy to take any more questions. And then if you have any questions in the future about any of this, of course, feel free to contact us. We're always happy to help get you started with these tools.
Thank you, Riccardo.
Hello, yeah. So I'm Ichi from MSc division. So I have 2 questions. First, rather simple. Will finally NECRS ML become open source or not?
It is. It's already open source. It's on the ALCF repository.
Okay. So another one is, I assume when you tightly coupled ML and NECRS is because you want to change the model when you machine learning can have some feedback to NECRS. So do you currently have some API to change NECRS model? Because I understand it's a little bit tricky to change NECRS model online.
Change it, you mean you have an ongoing simulation and you want to swap one for the other?
Yeah, for instance, if you would like to change the parameters of the model itself or the mesh size or something like that. Do you currently have these kind of capability, or you have planned to do that?
So that, I think, maybe goes more into that active learning approach. Maybe you could try to set that up with SmartSim. I think, though, it's not perhaps super well suited for that. You can feed a model back as you're training it to the database and then access that model through NECRS. So by basically, what is in NECRS ML right now is a plugin that has basically the building blocks for you to then maybe make more complicated workflows that feed information from the training back to NECRS. And the database should allow you to do this back and forth. But if you're trying to set up perhaps something a little bit more complicated where you need to submit multiple training runs at the same time, sort of do a model optimization problem, say, in situ, then perhaps trying to combine this with a workflow manager might be the best thing to do, and that's something that we are working on right now.
Cool, cool. Thank you.
Yeah.
Hi, I just want to make sure I understand correctly. So you train your model on the ongoing simulation. Let's say you want to try with lower and higher number. So can you then submit another one and train the same model, just expanding the training database?
Yeah, so that would be probably a case of sort of transfer learning. Another thing, though, that might be worth investigating is, can you run two simulations simultaneously, one at a low and a high Reynolds number?
Or more than two.
Yeah, and so they both are, or more, are feeding into the training data, so your model in a single shot is seeing both Reynolds number data, if
So
that makes sense.
Investigation error, right?
So basically here, instead of having a single CFD simulation, you can have two or three, and then the database is therefore filling up with, the entire distribution of training data that you're looking for. But definitely what you can do here is, instead of starting from random weights, is if you load in the model you've trained on previous data, then you can fine tune it basically to your current simulation, whether that's higher Reynolds number or even different geometry. Yeah.
Thank you.
Okay, in the interest of time, let's thank Riccardo again.